So to recap, blood's made of plasma and formed elements. Yes? Red blood cells, white blood cells, and platelets. So, platelets, another name for them is the thrombocyte. Do you know what a thrombus is? Nobody knows what a thrombus is? A clot, exactly. So what do you think these guys are going to help me with? Clotting. Very good. So, before I go on to the platelets, we left off talking about some white blood cell disorders. We left off talking about some of our friends in the white blood cell family that left the circulatory system and went into where? Who are these guys? Where do they go? Tissues. So monocytes can squeeze out of the circulatory system, go in, and become macrophages. Macrophages are phagocytic cells that hang out where? Speak aloud, I'm old. In the, what kind of tissues? Connective tissues, very good. So they hang out in connective tissues. We might find macrophages when we talk about the liver later on, digestive system. Macrophages in the liver are called Kupffer cells. And basically their job is very similar. No matter where they end up, they're going to be phagocytizing any particulate stuff. They might help with recycling those red blood cells if they're hanging out in the liver. Or they might get rid of old dead debris floating around or any particulate matter. B cells, T cells, both lymphocytes are going to help with what? Fight off disease, right? So they're going to be part of an immune response. We'll talk about them in chapter, I think it's 22, when we talk about the immune system. We'll meet these guys more up close and personal. But B lymphocytes leave the circulatory system, go into connective tissue, and become what? Plasma cells. What do plasma cells do for a living? They produce antibodies. And then the T cell can squeeze out and become something called an effector T cell. Another name for this guy will be the helper T cell. And when we talk about an immune response, you're going to meet this guy more up close and personal.
You said that one's like the cruise director, right?
Correct. That's my cruise director of an immune response. So it's going to help organize all of the other players in an immune response when we talk about that in chapter 22-ish. Okay? And then disorders of leukocytes is discussed in your book, leukemias. So if I start to see them change abnormally, what's a leukemia defined as? Cancer of what? Not bone marrow, but white blood cells. So what we start to see is the mechanism for maturation of these white blood cell characters is going to go haywire. Okay, way too many of them. Cancer. What is cancer? Yeah, the cells change somehow. And they change, they mutate, mistakes are made, and they no longer follow all the cell rules. Now, there's some very specific cell rules that all normal cells follow. One, if I have the ability to reproduce myself, I'm not going to reproduce myself unless needed. We don't want to get too crowded. We like to touch each other. Okay? In the case of these guys, not necessarily touch each other, but the crowded thing comes into play. Cancer cells don't follow the rules. They don't follow those cell rules. So they're just going to keep reproducing, whether they're needed or not. And the energy it takes for them to do that is going to be sucked up and taken away from what? Normal cells that need it. So what happens to the normal cells that have a specific function and do a specific job for you? They starve to death. Because the cancer cells, whose job it is just to basically make more of themselves, because they no longer follow the rules, suck up all the goodies. Yes? That's basically what happens. So, when we talk about leukemia, it's usually named for the specific leukocyte it affects. So we can have monocytic, basophilic, etc., 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 depending on what the cell type is that starts to go haywire in production. More serious acute forms primarily affect children. Chronic leukemias tend to be in elderly or older folks. Infectious mononucleosis, the kissing disease. What's that? Mono, what's mono? It's a nasty little bacteria. What's the name of the bacteria? Is it bacteria or is it a virus? It's a virus, exactly. It's called the Epstein-Barr virus. Yeah, and a lot of, when we get run down, or usually tends to hit younger folks, can hit older folks too. Yeah, and it makes you what? Very, very tired. One of the things in that white blood cell differential that we'll look at or see in a patient with infectious mononucleosis is an increase in what? What do you think? Yeah, in lymphocytes, believe it or not. Because lymphocytes are responsible for doing what? Fighting off those nasty little viruses. Sometimes people will yell out monocytes. It's like, no, that's not their job. Even though they call it that, mononucleosis, yeah, it doesn't affect those guys. So what we'll start to see is an increased number of larger lymphocytes, which don't typically look like the normal lymphocytes. So what the report will read, increase in number of atypical lymphocytes, because they don't look like they normally should. They tend to be on the larger side, and there tend to be more of them. So that's what we see in a patient with mononucleosis. Okay? So that little drop of blood can tell us tons about what's going on with patients. Okay, next. My friend, the platelets. Now, I talked about this cell a little bit earlier, last class. Again, all cells, formed elements, come from the same stem cell, hematopoietic stem cell, or the hemocytoblast. But the maturation process here, which you're going to have to know, which is stimulated by what? So erythropoietin stimulated that cell to become an erythrocyte. Cytokines, interleukins, colony-stimulating factors, that's what stimulated that cell to become the 5 different, what? That we just finished talking about. White blood cells, or leukocytes, right? What causes that cell to become a platelet? Nope. Some kind of chemical, there's got to be a message. What's the name of it? Remember what I told you the name of this guy was? Besides platelet? Thrombocyte. Thrombopoietin. Thank you very much. Who makes thrombopoietin? Kellogg's. Nope. Your liver. Your liver makes thrombopoietin. Patients with cirrhosis of the liver might have problems doing what? Clotting. They get a lot of bruising. Okay? because they have problems making enough of these guys. So thrombopoietin is going to stimulate the hematopoietic stem cell to mature into eventually what we see as fragments of this big giant mother of a cell, the megakaryocyte, which when it goes to squeeze into the circulatory system to become part of the circulatory system, what happens to it? It blows up. It's too big. So fragments of that megakaryocyte are what we see floating around in the circulatory system as a platelet. And platelets are very important for hemostasis. What the heck is hemostasis? Blood standing still, right? Or, give me another normal name for that. Blood standing still. Blood clots, yes? So when I cut a blood vessel, and similar steps to what we learned when we were repairing skin, we're going to see that there's a bunch of different steps that are going to allow us to repair the blood vessel. And who's going to be a major player in that patching up the broken blood vessel job? Platelets. So on page 646 in your textbook, we see the description of hemostasis, basically blood clotting. This is another positive feedback mechanism. Remember way back when, first semester, when we learned about the difference between negative and positive feedback mechanisms? This is a positive feedback mechanism. So in order to stop the reaction, what do we have to do in a positive feedback mechanism? In a negative feedback mechanism, stimulus, something happens, something changes, we're done. In a positive feedback mechanism, stimulus, something happened, something changes, we're not done. We're not done until what? In this case, we repair the blood vessel. In general, we need to remove the stimulus. Remember that? So we need to remove the stimulus. In this case, what's the stimulus? Big honking hole in my blood vessel, right? So this isn't going to stop until I remove the stimulus, or I plug up the hole. Very good. So vascular spasm is going to occur, and that is triggered by the release of chemicals from those damaged cells. So it's kind of like cracking an egg open and letting out a whole bunch of chemicals. Those chemicals are going to start causing smooth muscle contractions, causing vasoconstriction. What's vasoconstriction? Making them smaller. Step 2, those chemicals released that are causing vasoconstriction are going to do what? They're going to attract platelets. Remember one of the definitions of these white blood cells and formed elements was that word that began with a C? What was that word that began with a C? No. Drawing somebody to the area. Chemotaxis. Remember that word? So the chemicals in this case are going to draw platelets to the area, and they're going to actually cause them to be a little bit on the sticky side. There's a whole bunch of other chemicals that are going to help this process as well, but platelets are going to kick it off. So platelets are going to release chemicals once they get drawn to by chemotaxis, those broken cells, and they are going to cause other platelets to kind of bunch up and stick to the area. Now, they need a little bit of help staying there, because they might stick together, but we need to kind of somehow bind them together. So the third step is what we call coagulation. With the help of, and if you look on page 647, table 17.3, with the help of 13 different clotting factors or chemicals we are going to produce from that used to be soluble protein that was hanging out in plasma called what? Fibrinogen. We're going to turn it into a solid. And that solid is called fibrin. So with the help of platelets hanging out in the area, which are going to then get this chemical cascade of reactions going, we're going to form fibrin. And that's going to bind those platelets together and form that platelet plug. So the third step is called coagulation. Do you have to memorize the 13 clotting factors? No. You're welcome. You're welcome. When you go to medical lab school, yes, you do. But in here now. Just understand that there's a whole bunch of different chemicals, very dependent on a very specific chemical cascade of reactions we call the clotting cascade that are going to be important for forming that fibrin from fibrinogen. If I'm missing any of them, is it going to work? Nope. Another very, very important ingredient in this clotting cascade, and you have to know this, but you don't have to know all this nonsense, okay? What you do need to know about hemostasis and the pathways to prothrombin activation, and we see this diagram on page 648, what you do have to know is basically what's in the boxes, okay? These guys, not that guy. Those 13 clotting factors are extremely important. And they're extremely important to create this cascade of chemistry that will eventually make this substance. This substance, called prothrombin activator, is vital to forming the platelet plug, or the fibrin threads. Now there's two different ways that I can activate this clotting cascade. Again, this series of chemical reactions that involve the 13 clotting factors. Everybody with me? We can do it intrinsic or we can do it extrinsic. So do you have to know that? Yes. The intrinsic pathway, and we do this all the time. As blood is rushing through our blood vessels, the cells that line our blood vessels, and what do we call those cells? Take a guess. What do we call them? Endothelium. Very good. They're epithelial cells that line the inside of blood vessels. Just like our wonderful main roads in the wintertime, as we drive across them, and we plow them, and we shovel them, they become damaged, right? Okay, so the intrinsic pathway is going to help do road repair, basically, in the circulatory system. Platelets are going to be involved in that, mobilization of these factors, forming fibrin threads, but those are going to happen inside the blood vessels for road repair, basically. Excuse me, that's the intrinsic pathway, inside the blood vessels, right? That's one thing you could put in your notes. Intrinsic, inside. What if I come along and I punch you in the arm? What's a bruise? I came from the outside, right? And I caused what? The same thing, kind of a rupture of those blood vessels, or I cut you. Something happens from the what? Outside. That's the extrinsic pathway. So damaged tissue is going to release tissue factors. That's the difference between the intrinsic pathway and the extrinsic pathway. You with me? And that's a good one, because extrinsic outside, intrinsic inside. Okay. With the intrinsic pathway, we also see this PF2. Is it PF2 or PF3? It's PF3. Yeah, okay, good. PF3. That's going to cause platelets to come to the area. Tissue factors, that's what's going to cause that whole spiel to happen. Both of them are going to lead to what we call the common pathway. So whether we start the pathway intrinsic or extrinsic, they're both going to lead to the formation of what? Prothrombin activator. Now, just like we talked about in a second messenger system, when this chemical is on board, this substance is produced, it's going to trigger a chain reaction as well. The chain reaction it triggers involves phase 2 and phase 3 of eventually forming that fibrin mesh. Phase 2, prothrombin activator is going to come in contact with a chemical called prothrombin. And prothrombin 2 is going to then, with the combination of prothrombin activator, be transformed into what? Thrombin 2A. The presence of thrombin is then going to trigger the third stage. Thrombin 2A is going to come in contact with fibrinogen, and that's the stuff that normally just floats around in liquid form in plasma. But once we have thrombin coming in contact with it, it's going to transform it. It's going to transform it from fibrinogen to fibrin. And those fibrin are going to mesh together, cross-link, kind of suck in all those little platelets and form a what? And form a plug. Okay?
So they also have receptor, that's the phase 2.
Yep. They also, and remember, chemical reactions happen because of chemicals, the presence of different chemicals and the proximity of the cells. So this is the intrinsic and extrinsic pathway of clotting. So do you have to know that? Yes, but only the stuff in the boxes. There's a couple of other things besides the 13 clotting factors that form that prothrombin activator. Calcium is another thing. So calcium is kind of important. I mean, we've talked about it a couple times already, right? We talked about it when we talked about nerve impulses. We talked about it when we talked about muscle contraction, right? So calcium is important in reactions of metabolism in the human body. It's not just for making bones strong, yes? Another thing, vitamin K. Vitamin K is very important in clot formation. So that's another very important thing we need. If we have a vitamin K, not potassium, vitamin K deficiency, we can have problems with clotting. Okay? So understand those pathways. Once I'm done road repair, the clot helped me, it covered up the spot, I reproduced the cells underneath, I did road repair. Then I could just rip that clot off and throw it back into the circulatory system, right? No! How come? Because it's going to create a big plug somewhere in the capillary beds, right? So when I'm done road repair, what do I have to do? I got to break it down. So that's what they talk about under clot retraction and fibrinolysis. This is what it kind of looks like. There's a couple of interesting things here. So we have the fibrin mesh. You know what that is? That's a white blood cell. Got a bunch of red blood cells kind of all caught up in there. That's probably actually a platelet. It's too small to be a white blood cell. Isn't it cool? So clot retraction then has to happen. We have to use platelet-derived growth factors to help us do the opposite, dissolve. And that process is called fibrinolysis. There's a substance you might have heard of. It's called tissue plasminogen activator, or TPA. Has anybody ever heard of TPA? If somebody is suspected of being in the process of having a stroke, what do you do with them as fast as you possibly can? You bring them to the hospital, and if within a very short period of time, it's like 2 hours, you give them this tissue plasminogen activator, TPA. And what's TPA going to do? Break down clots. So this and the discovery of this substance externally given to patients has saved many, many, many patients from permanent damage from stroke. So if you can administer TPA quickly to the patient, you might prevent them from having permanent long-term damage by breaking down that clot. And I'm talking about, when we talk stroke, where does that plug happen? Yeah, typically in the brain region. But we can also use TPA for things like a clot in the lung or a clot in the leg. Okay? So very important substance. They talk about some of the different factors that limit normal clot growth. And again, if I have a missing piece in that cascade, it would be like me setting dominoes up on the table and then pulling out a section. This part would happen, but then it would stop because this part's missing. Those guys would still be standing up on the other side. So when we think of chemistry, think of it equated to those simple dominoes. If something's missing, it can't kick off the next step. So if I'm missing any of those factors, or if I have a vitamin K deficiency, or I don't have enough calcium, those are all factors that can affect the formation of clots. Hemophilia is a deficiency in, I think it's 13 or 10. I can't remember. Is it 13? So patients are missing that particular factor, unable to form clots at a normal rate. What could I give them to help them? I could give them a transfusion, but do they need whole blood? No, all they need is what? That little factor. They don't really even need platelets. They just need that factor. Where can I get it from? Your plasma. So one of the things that might happen to your plasma once it leaves that bag that you donated at the Red Cross, it might go to a lab where those factors are extracted from it, and then they're given to patients with things like hemophilia. Okay? So donating a bag of blood, it can end up being so many different things for so many different people. It's really worth it. If you can do it, do it. You know what? They give you free cookies. I donate for the cookies. There used to be Oreos. I'm a little upset now that Keebler Oreos. No, what's Nabisco? Nabisco Oreos aren't on the menu anymore, because that's what I used to go and donate blood for, is Oreos. Keebler. I miss the Oreos, I do admit, but it's still worth it. So if you can donate, it is definitely worth it. You can help many, many people. Yep. Plasmapheresis. There's a place in Portland, isn't there? Oh, that's right. I was going to say, I know there's Portland Biologicals, so that's in Lewiston. Yep. You can go and donate on a regular basis. It's really, really easy for the normal person to replace their blood volume. So if I give a pint, which is what I'm giving, of blood, it takes only a few days to make it up. And all you really have to do is what? Drink extra. Get some extra fluids into you. Plasma is even easier. You don't even have to make cells. Seriously, you're going to suck some more fluids out of places like, rather than kidney taking out that excess fluid, they'll just hold on to it to increase blood volume. So it's simple. So you can do that on a regular, you can do it once a week. you don't mind getting poked once a week.
So when we were talking about, I have this stuck in my head and now I need to know because I can't get it out.
Yeah.
Deep vein thrombosis. What is that?
So what would be the problem if I had a patient that for some reason caused that intrinsic pathway to kick in when they didn't need it? And what if that same patient formed those clots, and that's what your deep vein thrombosis person is doing. They're forming clots, exactly. Too many clots in too many areas. What happens if that clot breaks free?
Depends on where it goes.
Exactly. What do we call it now? It's no longer a thrombus, it's a embolus. And if that ends up plugging up some work somewhere, like here, or heart, or lungs, it can cause a big problem. So spontaneous clotting like that can happen when there's chemical imbalances. Exactly, and that's what I was just going to mention. So antithrombolytic drugs can be given to patients who might, because of different procedures or different, my brain just went dead. Yeah, disorders, thank you. Like AFib. Patients that have a flutter in their atria, because of that flutter, muscular flutter, it can cause spontaneous clots to form. Yeah, blood pooling in different areas, so different problems with circulatory issues can also cause blood pooling and clot formation. So, yeah, anything that messes up blood flow, high blood pressure, in severe circumstances could do the same thing. So patients are given antithrombolytics to slow down the clotting process. One of the most popular ones is something called Coumadin or warfarin or heparin. And they're given in different mechanisms. Heparin is an IV. There's a new one. I just saw a new one. Is that what it is? Cymbalta?
Well, Xarelto's
No, Xarelto.
In Canada, when
Yeah.
when we were in Canada, the doctors were terrified. They actually called Graham's doctor here to find out about it because it hadn't made its way.
Hadn't made its way there. But yeah, now that one seems to be, there's a lot of problems with regulation of diet with patients who are on Coumadin. Iron can be a problem. Like patients on Coumadin have to limit their intake of dark green leafy vegetables. They have to watch out for different foodstuffs like orange juice, believe it or not. So yeah, all the good stuff, broccoli, spinach. And this new drug doesn't seem to have as many restrictions, exactly.
Because it attacks soft tissue.
Yeah. So hopefully they'll get something better.
They say it's the drug you love to hate.
Yeah. The problem with Coumadin is regulating it. Because so many other things can affect it, cause it to be too good at its job. You don't want no clots to be able to form because that's not good. So constantly regulating the dosage based on dietary and is a pain in the keister. So yeah. So do you know somebody or yeah? It is. It's a pain, and so many different factors can affect it. If a patient goes on antibiotics, holy crap! Then you have to go through the whole spiel all over again. So. Right. You don't want, when I say doing its job too well, you don't want the patient not to be able to clot at all. So you have to get that fine balance of just the right chemical factors in your patients on those drugs. And that's a pain. That's a pain in the neck to regulate.
You gotta watch out for a fall.
Exactly.
I thought about cutting, but it's not.
So disorders of hemostasis are discussed. Thrombolytic disorders, liver imbalances can cause problems with the formation of thrombopoietin, and that can affect platelets. Anticoagulant drugs, aspirin, also causes your a decrease in thrombolytic chemistry. Too much, too little, platelets, hemophilias, chemical imbalances, disseminated intravascular coagulation. Again, it's clotting just popping up in places that it shouldn't, can cause all kinds of problems, especially if those clots get up and start to travel other places. Transfusion and blood replacement. So we've talked a little bit about the importance of donating blood. But I can't just give any blood to anybody. And the reason I can't just give any blood to anybody has to do with the immunogenicity of antigens. Oof, what the heck does that mean? All right, let's get back to simple. We have cells, yes? On all of our cells, every single cell in our body, we have plasma membranes, yes? And on those plasma membranes are not just phospholipids and cholesterol, right? We learned this way back when. We have a whole bunch of different proteins. And some of those proteins are actually like street signs for our immune system. They tell our immune system that these cells belong to us. We call them antigenic markers. We'll learn their proper name in a couple of chapters from now. They're called major histocompatibility antigens, MHC. So those are our street signs. Now those street signs allow us, A, to know what cells are our own, and B, to know what cells are not our own. Because your antigenic markers are not the same as my antigenic markers. One of the very important antigenic markers is the ABO blood group antigens. Now normally my body is only going to make something called an antibody against a foreign antigen if it comes in contact with it. So like I was sick a couple weeks ago, right? What happened to me? A nasty little critter, whether it be viral or whatever caused me to be sick, got into my body. My body recognized those foreign antigenic markers on whatever that nasty little critter was, right? And what did my body do? It waged war. So remember those white blood cells I talked about? They're going to work together. B cells and T cells, they're going to undergo what we call an immune response. And the B cells are going to be able to make chemicals very specific to that nasty little critter. What are those chemicals called? Antibodies. They're very specific to that particular virus that came into my body. And those chemicals are going to help neutralize that foreign substance. And then the other white blood cells we met are going to help get rid of that complex. But something strange happens with these antigens. Now there's 3 different possible blood types or combo of blood type. We can have antigens on the surface of our cells, and we're talking red blood cells here when we talk about the ABO guys, that are called A. We could also have an antigen on the surface of our cells that are called B. We can have a combination of them both. We can be AB. Or we could have neither of those antigens on the surface of our cells. That doesn't mean we don't have any antigens on the surface of our cells. We just don't have who? A or B. If I don't have either A or B on the surface of my cells, we call me type what? O. I got the ability to make or not make these antigens from my parents when they donated to me their genetic material. Now for every protein I make, I have 2 copies of information that I got from my parents. I got one from my mother and I got one from my father. The genes that we get that give us the ability to either make or not make these antigens, we call them I. Remember, I've got 2 of them, correct? All right. So I can have this one, or this one, or what would the other one be? I with nothing on it. We'll call it little I. Okay? Now remember, I've got 2 copies of one of these 3. Are we still following me? Okay. So if I'm type AB, what do my genes look like? Or if we're geneticists, we're not going to say, what do my genes look like? What are we going to say? We're going to say, what is my genotype? So if I have type AB blood, this is what my genotype is. Yes? So I have genetic information that I got from mother and father that allows me to produce proteins on the surface of my cells, both A and B. Now what if I'm type B? I have to at least have 1 copy of that, right? I can be this, or I can be this and still be type B. Yes? Because this one's going to let me make B, and that one's going to let me make B, or this one's going to let me make B, and that one's going to not make either A or B. You following me? What if I'm this? So if I'm 2 big I A, or I at least have 1 big I A's, I'm going to be type A blood. What if I'm this? So this is O, this is AB, this is B, and this is A. Now the reason I went through all of this is because I really want you to understand the principle of antigen and antibody. What is an antigen? An antigen is a substance that has the ability to elicit an immune response. And when I elicit an immune response, I make antibodies against that antigen. But we have antigens that belong to ourselves, right? Do we make antibodies against our own antigens? No. And normally we don't make antibodies against an antigen unless what? The antigen comes into our bodies. But for some weird, strange reason, and we have no idea why, we make antibodies, and just to these guys right here, we will make antibodies to an antigen that we don't have. And only when I talk about A and B antigens. We call them naturally occurring antibodies. And we have no idea why we have the ability to do that. So if I look at this chart, and I look at my players that I outlined here, type A, B, B, A, and O, when we donate blood from one person to another, we have to keep 2 things in mind. Not just the antigens on the surface of the cells, but we also have to think about the antibodies that somebody might have in their body against an antigen. So remember the naturally occurring antibody thing. So if I'm type AB, what type of AB antigens do I have on the surface of my cells? Both. What type of antibodies will I make to those antigens? None, because I have them both. I won't make antibodies to something I have. That would kill me, right? Because what happens when antigen and antibody come together? No, they form a big ball, a clump. Who's going to get rid of the clump? No, all those cells we talked about, the phagocytes. So the antibodies are chemicals that are going to plug up or neutralize antigens, and then other cells are going to get rid of it for us. If I'm type B blood, what antigens do I have on the surface of my cells? I have B antigens. Which one don't I have? A. So floating around in my circulatory system, I also have antibodies to the antigen that I don't have. I have anti-A antibodies. Yes? What if I'm type A blood? Which antigens do I have on the surface of my cells? A antigens. These words are very close together, so be careful when you read them. What kind of antibodies do I have in my circulatory system? Anti-B antibodies to the one that I don't have, right? How about O? Which antigen do I have on the surface of my cells? Neither A nor B. Which antibodies do I have floating around my circulatory? Both A and B, anti-A and anti-B antibodies. Well, here's the problem. Remember when my discussion of blood? What happens when you give blood? Patient doesn't get whole blood. Patients get what? Cells that I wash all the plasma off of, right? And I put in saline. I can give anybody my O cells, only if they're O negative, because there's another antigen we're going to talk about in a minute. It's called RH, or the D antigen. So these aren't the only ones we have to worry about. If I'm type A, I can only get what? Type A. Or, in a big pinch, some O negative cells. Because if you give me anything with a B antigen on it, what's it going to do? Form a big clot, make a big ball. That'll kill me. Type B. I can get type B. Or in a pinch, I can have some what? O negative cells. Do you see why I can have the O negative cells? Because they don't have any what? Those antigens, which I have antibodies to. If I'm type AB, so which would be, if I'm getting blood, type AB would be great, right? Because what? Well, I can get cells, remember that, from A, B, AB, or O. Now, what if somebody didn't understand the principle of antigens and antibodies, and they said, well, that guy's AB, I only have a bag of B, whole blood. We can just give that to him. What would be the problem there? The anti-A antibodies in type B blood would attack what? The A antigens on the surface of those cells. So you see what I mean? Only cells. So when we talk about this universal donor, universal recipient, it's only cells, not plasma. Okay? There's another antigen. Did they talk about it in your book? Yes. So ABO blood group antigens. We have to be careful with donating. We have to make sure that the blood will mix. No antigen-antibody reactions will occur when we talk about transfusion. Transfusions are typically not whole blood given. Very, very rare. It's usually packed red cells. Bless you! So there's another antigen we discovered later on down the line. It's called the Rh or D antigen. And that's the I'm A positive or A negative part of your blood type. Does everybody know their blood type? No? We'll do it in lab. But that antigen, if you have it, you're positive. If you don't have it, you're negative. And it follows the same rules of the genetics here. You have to have at least one copy to make the protein on the surface of the cells. But this particular antigen follows the normal antigen rules. So if I'm let's say a negative person, I don't have any anti-Rh antibodies floating around in my circulatory system. What's the only time I'm going to make anti-Rh antibodies? If that antigen enters my body. And then it's going to be just like when I get a cold. So the problem comes when I'm an Rh negative mother. And I'm carrying an Rh positive baby.
I was just going to ask you about this.
Yeah. Now, no matter how hard you try, no matter how easy the delivery is, during the delivery process, what's going to happen? Blood's going to mix. So the child's blood will get into the mother's circulatory system, no matter what, because we have that placenta break, right? So if you have an Rh negative mother that gives birth to an Rh positive child, what's going to happen to that mother? No, she's not going to bleed to death. Baby's blood's going to get into her, kind of like the virus got into me. It didn't kill me, did it? What did I do? I elicited, it felt like it was going to kill me at one point. But I elicited immune response. I neutralized the invader. And once I do that, I'm always going to have cells now that will constantly make those antibodies. And they'll be part of what I have circulating around in my circulatory system forever and ever.
Is there a possibility with one of those that the fetus will only be able to develop?
The first child will be okay. Yeah, everybody after that's in some big trouble. Because once you elicit that immune response and you create those antibodies are small. And guess what they can do? Yeah, cross over the placenta. During fetal development, those antibodies will get into that developing child's body. And if they start developing their blood cells with those antigens on them, what are the antibodies going to do? Attack them. Yes. So how can I prevent me, and we'll talk about this when we talk about immune system, but how can I prevent me from undergoing an immune response during that birthing process? No, not to suppress my immune system, but what if I pumped enough antibodies into you to neutralize any antigens that might come in? Will I ever elicit an immune response? No. So when I go, if I'm an Rh negative mother, and there's any chance, actually they just do it automatically now, if I'm carrying an Rh positive baby, they're going to give me something called RhoGAM. And what's RhoGAM? It's a whole bunch of anti-D antibodies. So I'll have plenty in my circulatory system to neutralize any antigens that get in, and I won't elicit my own immune response. The antigens will neutralize the antibodies, your phagocytic cells will get rid of all those, and then you'll just go on normal like you were before. So you won't make antibodies to that antigen. Not long at all. No. So usually, is anybody come across having to get RhoGAM or know somebody that, yeah, it's usually, right around the time of birth. They might give a couple shots, maybe even one after, but it's right around that whole process. They're not going to last long. Okay? So understand blood typing. If I want to figure out what my blood type is, what do? Simple. I go to the store and I buy the antibodies, right? So I go to the lab store, and that's what I did for your lab. I went to the lab store and I bought antibodies. How do I make the antibodies? Do you know? They're separated from blood. Whose blood? Goats! We pick on goats. We like to pick on goats. Bunnies, goats, those are usually the animals we pick on. So how do I make an antibody? How do you think I make an antibody? What am I going to give to the bunny or the goat? The antigen. So I take some A cells and I put them in the goat. The goat sees them as foreign. The goat undergoes an immune response. The goat makes what? Anti-A antibodies. Then what do? I go suck some blood out of the goat. Then I go to the lab and I separate out the anti-A antibodies and I put them in a nice little tube. And you go to the lab store and you buy them. Same thing with B. Same thing with what? RH, D. Okay? And then I take the antibodies that I made. I used to do this for a living in a past life too. And I put them on your cells. So if I have A antigens on the surface of my cells, and I add my anti-A antibodies to your cells, what's going to happen to your cells? They're going to clot. Antigen-antibody reaction. This person is type AB, so it would do the same thing with the anti-B antibodies. If I put them on there and the antigen is present, they're going to form a clot. If I'm type A blood, the only clot we'll see is when I put anti-A antibodies on there. Will I see anything with B? No. Why? Because there's no B antigens there. If I'm type B blood, yes? And what if I'm type O? Nothing. Yes? It would be the same kind of test using your blood and anti-D antibodies or anti-RH antibodies. So if I had them, if I was RH positive, what would happen to my blood? It would clot. If I didn't have them, what would happen to my blood? Nothing. No. It's a third test. So we should put a third ball there. Right? So you have neither A nor B antigens, on the surface of your cell. But if I put that third test up there, that would be clotted. So you have the D antigens on the surface of your cells, or RH antigens. So when I put the anti-RH on yours, it's going to clot. So when we go to the lab, we can test yours, and we can see no clot, no clot, clot. So you got nothing. Yeah. But O negative is desirable for who? Everyone else, right? Yeah. They love it when you come to donate blood, right?
I could only give blood to O positives.
Correct. So O is the person that's not so happy when it comes to blood receiving, right? Because you can't get any A or B cells in you. If you get A or B cells, what are your antibodies going to do? Attack. Right? So you're on the receiving end, you're screwed. Because all you can get is what? Type O negative. He can't even get O positive, right? It tends to be more rare. Did they give you percentages in the book? Yeah. A and O tend to be higher in the percentage. Depends on the area. And basically, genetics. What group of people pass their genes to these groups of people.
And the O, right, because it's more widely used, because it can be used, there's always a shortage of it, right? Isn't that it too?
Well, and it depends. There tends to be a lot of people in the population that have type O too. So it depends on your population, where you are, as far as what you have on hand. But you should definitely be a blood donor on a regular basis, right? Yeah. Who doesn't donate? Who's afraid to donate blood? They won't take yours? Well, if you have certain disorders or you're on certain medications, don't donate blood. Because you don't want to give that to somebody else, right? But if there's no reason,
What if you have like low blood pressure?
yeah, they tend to stay away from you. They don't want you passing out on them.
I do.
Yeah, yeah. But if you have no real excuse, you get scared. It's a little 19-gauge needle.
Yeah, but they miss and then there's just bleeds everywhere.
It's just 19. And you get free cookies! Cookies and juice. What is better than this? Yeah, pizza and beer. Pizza and beer would be good. That might draw more people into the donor booth. Good?
My boyfriend has valves in weird spots in his veins, so he tends not to donate because every time he does, they.
Well, valves aren't a problem. It's the person taking the blood that's the problem. Okay, so here's the deal, my dear friends. We can have 2 test scenarios. I will offer them both up. I will allow you to vote on the scenarios. Your exam will be on Tuesday of next week. Chapters 15, 16, 17. Scenario number 1. Get it done, get it out of the way. Or I can go on, lecture you on the next chapter, and wait till Thursday. Either one, I'm easy. I would highly suggest you take it on Tuesday, get it over with, and be done. Yes?
Yes.
So who would like to start the vote? Scenario number 1. Your exam is on, okay, easy. So your exam is going to be on Tuesday of next week. Chapters 15, 16, and 17.
Will we have a quiz this chapter?
Correct. Where am I? From beginning. No. What am I doing? So I will open up the quiz, and it'll be due, you know what? I'm going to have the quiz due Sunday. And I know, when. But the reason, listen to my reasoning. The reason I'm going to have it due Sunday is so you can review it before, okay? So I'm going to have the quiz due Sunday. That way you'll have Sunday and Monday to review it, just in case there's something on there you want to go back. You have the essay questions, yes? After centrifuging of the listed blood components, which contains the components of immune function? Did everybody bring their clickers today? So make yeah, send me an email. Otherwise, you're going to get marked absent. And I have Michelle's clicker number. Did everybody give me the clicker number that night, that day? Did you give me yours? No. Just before you leave, write it on my little thingy. So I'll make sure everybody matches up. So we only have 22 clickers in the house today. 23, 24. 4, 3, 2, 1. What's the, wait a minute. All right, what's the answer? No. The answer is, oh yeah, because, okay. B, I think it would be plasma. Yeah, that's a bad question. That's a bad question. It actually, I mean, if you think about it, where are all your clotting factors? They're in plasma, right? So that's a bad question. All right. No. Where the heck is my, pick my answer? Third one. There it is. It says B, but I say A. I say that's a bad question. I wouldn't ask you that question. A major function of the most common plasma protein albumin is what? All right, number 24. Push your button. Oh, it's 25? Uh-oh. All right, what's the answer? D, both.
So I was half right.
You were half right.
You don't post these questions, do you?
Nope.
You can see them after.
Nope, you can see them when you watch the video. See?
So we can't see them.
Yeah, they're on the video. Red blood cells are efficient oxygen transport cells. Of the following characteristics, which is the major contributor to the significant oxygen carrying capacity of a red blood cell? What allows it to suck up more oxygen? Basically is the question. All right. Everybody push? Everybody push again. It was 25 last time? Uh-oh. Is everybody's clicker on? Make sure it's on. All right. What's the answer? The answer is C. Very good. See, because that thin area allows for easier gas exchange. So nobody picked A or B. Very good. All right, another one. Each hemoglobin molecule can transport how many oxygen atoms? Each molecule. How many seats on the Ferris wheel? Five, 4, 3, 2. You think it's more than 4? I say it's 4. Remember, no, there's 4. Remember, 4 quaternary protein, 4 hemes. Yeah, see, you're like, no, it's got to be more than that. Nope. No, it doesn't. Remember, there's only what? There's only 4 seats on the hemoglobin Ferris wheel. Only 4.
One little chair. It's not the whole Ferris wheel, it's just a little chair.
Right, only 4 chairs on the Ferris wheel.
She was thinking.
It's a small Ferris wheel. It's very small. Got it? That is a pretty good analogy. Oxygen binds to what portion of hemoglobin? Question is, oxygen binds to the what portion of hemoglobin? Where's the chair? Where's the chair? On the heme molecule, the iron atom. Oxyhemoglobin is what you call it. When oxygen binds, that's not the place. And globin is the what? That's the protein part. That's not the seat. Ooh. We even had an E in there. That's interesting. We're just adding letters now. All right, a patient with low iron levels would experience which of the following symptoms? Damn it, I got this one. So if I don't have iron, what can't I make? I can't make enough heme. And I can't carry enough what? And if I can't carry enough oxygen, then I can't get lots of energy. I'm very tired. Hematopoietic stem... Ooh. D. Hematopoietic stem cell gives rise to everybody. Oh, this is a tough one. What the... All right. Predict the outcome of an overdose of the hormone erythropoietin. Come on, that's an easy one. What? Reticulocytes? With a wand. Reticulocytes. All right, we good? Come on. Come on, this one's easy. All right, what's the answer? The answer is A. Blood becomes thick. Now look at the answers here, okay? Too much erythropoietin equals too many what? Red blood cells, okay? Oxygen carrying capacity remains unchanged. Wrong, now I got all these red blood cells, I'm going crazy with the Ferris wheels, right? Red blood cell counts remain unchanged. No. Blood viscosity levels decrease. No, there's more cells in there. It's going to get thicker. Yes? All right, one more question and then you can go away. What response would you expect after traveling to a high altitude for 2 weeks? It's going to be harder for me to carry oxygen in a high altitude. Hint. What's the answer? If it's going to be harder for me to carry oxygen at a high altitude, I'm going to need to make more what? I'm going to need to make more red blood cells. In order for me to make more red blood cells, I need to have more You get it?
After 2 weeks, you should be out.
Yes. Okay, my friends, test on Tuesday. Unless you're in the hospital, you better be here. And if you are in the hospital, I want a doctor's note. I want proof. I want pictures if necessary. Oh, wait a minute. Let me, otherwise you're going to